So the last two lessons of this unit, we actually want to look at two methods of approximating values, okay? And maybe you've wondered at times, you know, how did they do stuff like, what's the square root of 4.1 or something like that before we had our nice calculators to do it for us, okay? And there are certain algorithms that people have used over the years to find things for like a square root or whatnot. But one of the methods that we can use are these approximation methods using the derivative, okay? And this first one here that we're looking at today is the tangent line approximation. And we have a little exercise we want to do, and that's we're going to graph on our calculator this function 1 plus sine of x. Okay, so if you'll get your calculators out and put that in, let's take a look at that. Okay, so I'm going to bring up this, we're going to take a video of this. Okay. Alright, so we'll move this over here so we can still see. Alright, and we hit graph. We got our windows set. Alright, so now we have this. There's from negative pi to pi, and it's what we would expect, guys. It goes from 0 up to 2 because it's been shifted up 1. Alright, at negative pi, 0, and pi, it all equals 1 because it's right on that center line. Okay. Notice it also says we want to also graph the tangent line. Okay. Well, the tangent line is going to have a slope of 1 because the derivative of f of x, is cosine. So f prime of 0, we want it to hit that tangent line 0, 1. F prime of 0 is cosine of 0, which is 1. And since we're hitting the y-intercept anyways, we know that the equation is y equals x plus 1. Or we can look down at the table since we have guided notes, and there it is right there. Okay? So I'm going to go back and I'm going to graph that as well. 1 plus x. And there's the line. Now, you can kind of see already when it gets close to this point 0, 1, the point of tangency, it looks like the line is right on top of the function and they're like the same values all around there. The directions tell us to zoom in twice, so we're going to hit 2 for zoom in, get close to that point of tangency and hit enter, and it'll adjust my window. Why is it not doing that? Okay, let's zoom in, enter. Okay. So there's the sine curve. Remember that was on mine, it was the blue one. And here comes the line. Ooh, that's really close. All right. Now we could do this again, but I think we can get the picture just from this. Yeah. So I'll stop this right there. So notice here, does our graphing utility distinguish between the two graphs? Other than the fact that we can kind of see blue and kind of see red, no. All right? And the whole point of this is the fact that as we are looking at this, the more we zoom in, the closer this line is going to give us values of the function. Yeah. Okay? And this is why we call this a linear approximation. Okay? Now, if we were to use this table, we can obviously fill in the second line just from what we know. Okay, if we do 1 minus 0.5, it's 0.5, 0.9, 0.99, 1 minus 0 is 1, 1.01, 1.1, 1.5, okay? But let's actually use our calculators and go to the table, or actually if you just hit trace, you can type in different values. So I'm going to trace on that 1 plus sine x. If I do a negative 0.5, I get 0.52057, okay? 0.52057. If I put in a negative 0.1, I get 0.90016. And so on. If I put in a negative 0.01, I get a 0.990000, bunch of zeros. What, 3, 4? 4 zeros before I have a 1,7. Okay? This part you can do because you know it. Sine of 0 is 0, so 1 plus 0 is 0.
How do you come up with the bottom?
That's our tangent line. That's the tangent line hitting the point 0, 1. Okay? So we're, the derivative was cosine, so the slope of this at 0 was cosine of 0, so 1. Okay?
I know.
If we keep going here, 1.009998. 99998. And this is 1.0998.
And then 5 is 1.4794.
Okay? All right, so we have that. What do you notice about the value of the function compared to the value of the tangent line as we get closer to this point 0?
They get more similar.
They get more similar. They're closer and closer together. And the idea is this, guys. While we do recognize that there is a slight curve on sine, the tangent line, because we're so close to it, the tangent line will give us a very close approximation as long as we're close to where x equals 0. Okay? That's the whole point here. Now, there's this formula down here. The equation for the tangent line at a point C f of c can be given by this, all right? Now, this is just point slope form, if you think about it. The slope is f prime of c. The point we know is c f of c, okay? Now, again, one thing to make sure you recognize here is that this point c f of c needs to be a point that you know or can figure out easily, okay, without using a calculator. So this is the point you know. All right?
So if you don't know it, if you can't find it easily, you can't use it in your approximation?
True. True. Yeah, you have to have something that you're able to figure out. But every function has at least some point somewhat close to where you want to be that you could figure out. Okay? Now, x is the value you want. All right? We want xy to be the point you want to know. And the idea is this: as x approaches this value of c that you know, the value of the tangent line is going to get closer and closer to the value, the actual value of the function. Okay? So this is what we could do with this. We knew this point 0, 1. So as long as I keep x really close to 0, I can approximate what the 1 plus sine of x will equal. All right, so this is what we're using this for. Approximate f of, let's say, a 0.02, since we didn't do that one on the table up there. Okay, now because I have this table, I know it's going to be somewhere between 1.0099998 and 1.0998. All right, but what actually is it? Well, I'm going to say that this is going to approximately be 0.02 plus 1. Remember, our tangent line was y equals x plus 1. Okay? We already found the tangent line, so we could just plug in a 0.02. So f of 0.02 is going to be approximately 1.02. If you actually did this on the calculator, you would get f of 0.02 equals a 1.0199987. So what, we're 1,300 thousandths off? I think I'll take that level of accuracy. Okay? Is that 100 thousandths or is that millions? Tenths, hundreds, thousands, 10 thousandths, 100 thousandths, millions. Oh, that's 10 millions. We're 10 millionths off. Yeah, that'll do. Okay, unless we're going to space, that'll be good enough.
Y equals 1. What are we finding?
We're finding an approximate value of this function, 1 plus sine of x. Let's do another example, not with this tangent line, but let's say that I wanted to approximate, we'll go down here. What is f of, let's do pi over 6 plus 0.01. Okay? So, whatever that is. Okay? Well, let's use that formula because I don't have the tangent line here yet. All right? But I'm going to say that that's going to approximately be a point that's close to it. All right? Now, what's the closest point I know on sine of x plus 1? Well, we know one closer than that. F of
0.0001 something?
no, come on.
0.002.
How about pi over 6?
Oh. Yeah.
Okay?
Yes.
That's all right. F of pi over 6 is going to be 1 plus sine of pi over 6. What's sine of pi over 6?
1/2.
Yeah, okay. Whoop, not pi over 2, pi over 6. All right, so this is 1.5. All right? So I know that, again, using this point slope form with my derivative, I know that f of pi over 6 plus 0.01 is going to approximately be 1.5 plus the derivative. The derivative f prime of pi over 6 times the x value that we want. So it's pi over 6 plus 0.01 minus the x coordinate. Well, the x coordinate is pi over 6, right?
Yes.
So notice the point that I want, the point that I want is the point where x is this. Okay? The point that I know is pi over 6, f of pi over 6. Okay? I know my numbers kind of ran into each other here a little bit. But now notice this is something that we can figure out. It's 1.5 plus, okay, the derivative we already said was cosine. What's cosine of pi over 6? Square root of 3 over 2. Okay? Now, pi over 6 minus pi over 6 is 0, so I just have 0.01. Okay?
Yeah.
That right there, this times 100th, that's going to be a root 3 over 200. 1.5 plus that will give me an approximate value of the sine of this plus 1.
Which is gonna be
Okay.
300
As a decimal,
times root of
Well, would we?
Root 3 over 2.
1.5086.
Okay.
What do we even?
what does it come out to?
1.5086600254.
0254.
Yep.
Okay. Now, question. On the original function, if we're tracing, let's say I type in pi divided by 6 plus 0.01. I actually get 1.5086351.
Oh.
Okay?
We'll
That's
write
what
that
it
down.
actually equals using the calculator.
So is it better to use the calculator?
Yeah.
Well, yes, but think about what we have here. We have a situation, and this is how people came up with tables and things like that. They used tables in the past. For example, before we had the calculators that could tell us what sine of this was, we had a table where people had used different algorithms to figure out what the sine of, say, we'll go with degrees just to make it easier. We had a whole table that said, hey, sine of 47 is this, sine of 48 is this. Well, what if they needed 47.3? They would actually use the two values in the table on either side and do what's called a linear interpolation or linear approximation and just do kind of a proportion between those two values. And what they were doing is they were assuming temporarily that sine was a straight line within those 2 degrees. Okay, and they were close enough together that we got a really good approximation for it. Okay?